I'm very happy to introduce our speaker today. Well, he doesn't need an introduction now, since he already spoke in the seminar earlier in October. And this is Christophe Prange from CNRS, Sergi Paris. And today he will tell us about his second topic that he has been working on for a few years now. And this is boundary layers and homogenization. And specifically, he will talk about quantitative asymptotic analysis and large-scale regularity. Over to you, Christophe.
Yeah, so thank you, Kirill, for the introduction and for the kind invitation. I'm just wondering now, can you see my screen, because
yes, it's perfect. It's
okay,
perfect.
Okay.
Yeah.
Okay, good. So I'm going to talk about boundary layers and homogenization in two perspectives. So the first one is the quantitative asymptotic analysis, and the other perspective is about large-scale regularity. So my collaborators on this, so it's a long-term work in collaboration with Scott Armstrong, Tuomo Cusi, and Jean-Christophe Moura for the first part. And the second part is with Mitsuo Igaki, who used to be a postdoc in Bordeaux and who is now assistant professor at Kobe University, and Carlos Koenig, while I was there in Chicago. So let me just introduce quickly the two topics that I'm going to talk about. So the first one is about homogenization of uniformly elliptic divergence form equations with oscillating coefficients. So I'm going to take periodically oscillating coefficients and oscillating directly boundary conditions. So you have oscillations both in the boundary condition and in the elliptic operator. So I will explain in a minute where this problem comes from, originates from, but let me just mention quick remarks about this. So the problem was actually identified very quickly in the homogenization theory. So in the early developments of in the 70s of homogenization theory of periodic composite materials, Bensoussan, Lyons, and Papanicolaou in particular identified this boundary layer problem as a key problem to understand the asymptotics up to the boundary for solutions to elliptic divergence form equations. So, so this is the first system I'm going to focus on, and I will be interested in quantitative homogenization for this equation. That is, I'm going to derive the limit of the U epsilon BL in certain domains and also compute or derive error estimates. So the second topic will be about regularity theory. So regularity theory will be really central to the talk because it's going to give estimates that are also useful for the study of boundary layers. But this second part will be specifically devoted to proving regularity estimates. And the type of problems we'll look at is when you have a domain with a highly oscillating rough boundary. So for example, you take a Lipschitz highly oscillating boundary, and we will ask about the regularity of solutions to certain PDEs. So it could be an elliptic equation with oscillating coefficients, for example, representing a composite material, or the Navier-Stokes equation, or any fluid equation you'd like. So we'll focus on fluid problems, that is Stokes and Navier-Stokes equations in these bumpy rough domains. Sorry for that. And so, so one thing people are usually interested in is, of course, asymptotic analysis of the problems when their height or their amplitude of the oscillations of the boundary goes to 0, epsilon, and when their length scale of the oscillations goes to 0. And here in the whole talk, we'll take the same amplitude and as the length scale. So one thing people are interested in, of course, is asymptotic analysis and concerting error estimates, concerting expansion and proving error estimates, and in particular deriving fictitious effective boundary conditions, which are called wall laws, on a fictitious boundary that would be smooth, flat, replacing the rough boundary. So the idea is, of course, motivated by numerics. For example, when you don't want to solve explicitly all the small scales, but just you would like to replace the model by something easier to compute. And the questions we'll be interested in is large scale or improved regularity. So we have all these oscillations and small scales close to the boundary, but we would like to see if away from the boundary we can derive good regularity estimates. Okay. So I will start with the, sorry for that. I will start with the study of boundary layers, and just to give you a quick introduction about the history of the boundary layer problem. So, so if I go back to the early developments of the periodic homogenization, dating back to the 70s with the work of Lyons, Papanicolaou, and Bensoussan and others, and you look at the problem with oscillating coefficients and Dirichlet boundary condition, just homogeneous Dirichlet boundary condition. So you write an ansatz, a two-scale ansatz with the macroscopic scale x and microscopic scale x over epsilon. And of course, you find the homogenized limit u bar, and then the first order term, which has this separated structure with the oscillating cell corrector and the gradient of u bar. Of course, u bar solves the homogeneous equation, and the cell correctors are the chi's, the function chi's that are periodic and that make the function y. So the function y, of course, is not a solution to the equation, but the chi is the corrector that makes y plus chi be a solution to the equation. So we say that y plus chi is a linear or a harmonic function. And so once you have this, you can derive error estimates for the difference between u epsilon and the first order approximation. And of course, if you have some smoothness on the u bar, on the limit problem, then, sorry, I just spotted a mistake here in this slide. It's the homogeneous equation. You should put the right-hand side f, of course. So it's not 0, it's f in the right-hand side. And so if you have some, and with homogeneous directly boundary condition. So if you have some smoothness on U bar, then you are able to derive error estimate. So this first error estimate is away from the boundary. So there we get epsilon in H1. So now, if we write the estimate up to the boundary, we lose epsilon 1/2. So we just get epsilon 1/2 in H1. And the reason is that there are, in the region omega, so the whole domain minus the interior, there are strong gradients, so making the H1 norm big there. And the reason for these strong gradients is that there is a boundary layer, and you can capture these strong gradients by introducing this specific boundary layer function, so U epsilon BL, which satisfies the problem with oscillating coefficients, so the divergence from elliptic equation. And on the boundary, you put exactly the quantity that kills the oscillations of the first order corrector. So this expansion U bar plus epsilon chi x over epsilon gradient U bar, that one was derived by considering the microstructure, but completely ignoring the boundary. So that one is really suited to the microstructure of the problem with this periodicity at small scale, but it's not at all adapted to the boundary value problem. And so this expansion here misses the behavior of U epsilon close to the boundary. And this is what we try to correct by introducing this boundary layer corrector. So this boundary layer corrector, if you have sufficiently smooth boundary, you can have uniform LP bounds. But if you look at the boundary layer corrector in H1, you have strong gradients. So the gradient in L2 is of order epsilon minus 1/2. And so if you introduce, this is epsilon minus 1/2 is the reason why you lose epsilon 1/2 in the right-hand side of your estimate. Okay. So now if you, so the first estimate is the one we already looked at. And now if you take this boundary layer into account in your expansion, at first order, you can recover the epsilon you had before, okay? Because now this boundary layer function that you introduced killed the strong oscillations due to the first order corrector. So you restore the good approximation, but of course you have this corrector here, U epsilon BL, which is a bit artificial for the moment and on which you don't have information. And of course, if your goal is to compute numerically things, it's completely ineffective for the moment because you just introduced artificially a corrector that widely oscillates and that you, for the moment, have no idea about the way it looks. So it is crucial to get the asymptotics of this U epsilon BL. And as we will see, this problem is difficult and has a lot of interesting behavior. And so a last error estimate is the one that I mentioned here, which is now in L2, and which is obtained by writing the asymptotic expansion up to order 2. So instead of writing up to order 1, I write the correctors of order 2, epsilon square. And then I measure in L2, so the correctors of order 2 will be of order epsilon square in L2. And I'm left with this estimate here with an epsilon square in the right-hand side. So the idea here is that if you have this estimate and the asymptotics of U epsilon BL in L2, then you can replace U epsilon BL by the homogenized one. Okay, so yeah, let me just mention that this bundle layers and their asymptotics also appears in a lot of work on eigenvalues, because the first, so if you try to have an expansion of eigenvalues to an elliptic system with oscillating coefficients, periodically oscillating coefficients, then the first order correction, so first order in epsilon, if you fix the mode, will involve boundary layers. So how can we tackle this boundary layer problem? So one natural way is to try to see what is happening close to the boundary, because this boundary layer corrector is really there to correct the bad approximation, the bad two-scale expansion close to the boundary. So its effect is really crucial close to the boundary. So you want to understand what is happening close to the boundary. So you simply blow up close to the boundary. And of course, if your boundary is sufficiently smooth, the problem that was in the domain omega becomes a problem in the half space. And so we get some sort of cell boundary layer problem that is posed in a half space, directed by the normal at the points where you blow up. And so we'll see later on that this cell boundary layer problem says a lot about the dynamics of the real boundary layer defined in the domain omega. So the difficulty here is that, okay, we blow up close to one point, we get a boundary layer cell problem, which is posed in half space. But of course, you get a different problem depending on where you blow up on the boundary. And so you get, in the end, an infinity of boundary layer of homogenization problem. And so that's one problem. So the one question is how to glue these problems together to get something. And the second problem is that the boundary breaks the periodic structure of the problem. With that, I mean that if you look at the oscillations of the G, so G is periodic in Y, in the fast variable, because it comes from the cell corrector, chi. And if you look at G along the line passing, or along the hyperplane passing through x0 and tangent to partial omega, you don't get periodic oscillations, you get quasi-periodic oscillation, because it's the restriction of a periodic function to a lower dimensional hyperplane. Though the problem, the structure of this homogenization problem, or of this cell problem, is quasi-periodic and not periodic. And this is another difficulty of the problem. So we have seen 3 difficulties of the boundary layer problem. If you want to look at the asymptotics of this U epsilon BL, one difficulty was the lack of uniform bound in H1. Second difficulty is that you have an infinity of such problems, boundary layer problems, as half-space cell problems. And third difficulty is the lack of periodic structure. So, and this, with this lack of periodic structure comes some phenomenon which we call resonances. That is that, so this picture is coming from a numerical simulation from Antti Hannu-Kainen, who just simulated a constant coefficient equation with an oscillating boundary condition. And what you see is that these these parts close to the boundary with these peaks corresponds to the boundary layer. And so you see that the size of the boundary layer depends on where you are on the boundary, and is not uniform. Okay, so you have some places here, for example, where the boundary layer is bigger, and some places here, for example, when the boundary layer is small. And this comes from the fact that these are half-space cell boundary layer problems that I was mentioning do not behave the same for different ends. And there are some ends for which you have resonances, and some ends for which, some normals for which you don't have resonances. And this is something we have to look into detail into, and which we'll do in a minute. It's a very interesting phenomenon happening in this boundary layer problem. Okay, so now let me shortly discuss our different scenarios. So the first scenario is when n is a rational number, a rational normal, meaning proportional to a vector in ZD. So there are many works about this situation, dating back to Lyons. So I've read some works here, but they are far from being exhaustive about this periodic case. And in the periodic case, you, sorry, in the rational case, the restriction of the boundary condition to the hyperplane will be periodic. So I said that before, that in general it's quasi-periodic. Here it's going to be a periodic problem, and so you can just work in periodic cells along the hyperplane tangentially, and so periodic cylinders if you want. And so you have this periodic structure, and so you have Poincaré inequalities and etc., etc. So you can solve the problem and work easily. And because of this simplification, the problem was studied much earlier. And so there is I'm not aware of many computer simulations in this case, at least in the mathematical literature. There is one by Versio and Sarkis showing that the computation of the asymptotics of U epsilon with the corrector. So on the left is the real solution U epsilon. On the right is when you just consider U epsilon minus the first order approximation, ignoring what is happening on the boundary, so the interior approximation. And the third picture is the one where you subtract the boundary layer. So here you see that on the second picture you have some larger region close to the boundary, which corresponds to the fact that the boundary layer is not captured. So there is a clear limitation to this computer simulation that dates to some years ago already. Probably even at that time was possible to do better than this, but here you take an epsilon, which is 1/20. So the difference between the picture in the middle and the picture on the right is not so big, right? Because here you have like 0.8 or 10 to the minus 3, so 8 to 10 to the minus 4, and here you have 4 to the minus 4, 10 to minus 4. So it's not, adding the boundary layer here is not that spectacular, but it's the only computer simulation I could find in the literature. Okay, so but we still see a little bit of the boundary layer not being captured. Okay, so now the case of the generic case of irrational normals. So there was intense activity starting from 2010, and in particular due to a breakthrough result by Gérard Varé and Masmoudi in the years 2011-2012, where they were able to use the quasi-periodic structure that I was mentioning of the cell boundary layer problem to study the well-posedness of the cell boundary layer problem and to study the asymptotic properties. So they used an idea similar to Kozlov when he proved the existence of cell characters for so interior cell characters, the Ks, for structures that are quasi-periodic. And so, well, basically, so I will come to this later again, but basically, since you have a quasi-periodic structure, you can lift your problem to a higher dimensional torus and then work there and study the system there. And since you work in a high dimensional torus, you will have a periodicity and Poincaré inequalities, etc., which enable to work. So what they proved is first they studied this boundary layer problem in the half space, and then they glue things together and get the convergence of U epsilon BL to a U bar BL, a homogenized one, with homogenized boundary condition. So they identify a G bar, which is called the homogenized boundary condition, and prove estimates between U epsilon BL and U bar BL. And this they do under geometry, a condition on the geometry of the domain. So that under the condition that omega looks like a disk, basically. Okay, so let me now spend some time about the half-space boundary layer problem, which is really fundamental. And then we'll see how to glue things together. So, so during my PhD, I studied the half-space problem without, so this is the cell problem. And I studied this problem without assuming any thing on the normal. So the normal could be rational, irrational, etc. And my goal was to prove that the V, the capital V, was converging to something at infinity, at space infinity. So I was using results by Avelandeda and Lin, which are results about uniform regularity for operators with oscillating coefficients. And these results enable to get the asymptotics of the Poisson kernel. So the Poisson kernel associated to this problem. And you have an explicit, so you have a P bar, which is the homogeneous Poisson kernel, and an explicit omega, which is which has a periodicity in Z. So you can use the properties of this omega to study the convergence. So here you have this product of omega times G on the boundary of the half space. And so this thing here will converge when y dot n goes to infinity. So that is when you go away from the boundary of the half space by an ergodic theorem. And so the limit of the V will be a constant, which is the one written in these brackets. And this limit is called the boundary layer tail. So the boundary layer tail will play a role when identifying the G bar, the homogeneous boundary data. So now it's time to talk about resonant versus non-resonant directions. And in particular, what I will be interested is here, I told you I have the convergence, okay? But I didn't tell you at what rate. So what I'm interested in now is about the rate of convergence. And it turns out that the rate of convergence depends on the normal n and on the speed at which the torus will fill. So let me explain a bit about this. So on the right, you have an n which is rational. So if you draw the line on T2, you will not fill the whole torus, okay? It's periodic and you just travel on the same parts of the torus, but always on these lines, okay? But you don't fill the whole torus. Now, if you are irrational, then the lines will fill the whole torus in the end. But the convergence or the speed at which you fill the whole torus may be arbitrarily slow, depending on n. And now to study quantitatively the boundary layer problem, so the asymptotics of U epsilon BL, you need some quantitative estimate for the speed of convergence. So specific directions will play a role. And these specific directions are the ends for which you have a non-resonance condition. So the ends which we call Diophantine or non-resonant, which are ends which are irrational, and for which there exists an A such that for any psi in ZD, the projection of psi on n perp is bounded from below. And so A of n will be the optimal constant if n is Diophantine, and if A of n is 0, we call this a resonant or not Diophantine direction. So this condition gives you some sort of lower bound between the hyperplane n perp and the points of ZD. And if you have this Diophantine condition, then you can have a speed of convergence in the ergodic theorem, and the convergence will be faster than any polynomial in y dot n, so in the distance boundary. So so now in 2012, as I told you, Masmoudi and Jaravare were able to study the problem, the cell boundary layer problem, using the quasi-periodic structure. So now they don't rely on Poisson kernel, but they rely on energy estimates for V and the derivatives in a high-dimensional torus. So what they do is they use the fact that the boundary condition is quasi-periodic along the hyperplane, so the restriction of a periodic function along the hyperplane, and so they lift the problem to a torus times a segment A infinity, so a higher dimensional cylinder, if you like. And so if you lift the problem to this high dimensional cylinder, the real derivative in y is replaced by this the general derivative in the horizontal direction, and dt in the vertical direction. So you get this a bit strange problem with the general derivatives. So it's an elliptic problem, but with a degenerate derivative and periodic coefficients in theta. But now, so of course, if you are able to construct this curly V, then you have a solution V to your original system. But now what you lose is the fact that this derivative is degenerate, but what you gain is compactness in the horizontal direction in theta, and periodicity, and so Poincaré inequality, spectral gap, etc. So from there you can control the high dimensional derivatives just doing energy estimates, and get the speed of convergence when the n is Diophantine. So the energy estimates here, you can do that for any normal, but the speed of convergence of the derivatives you can only get when the a of n is positive. Okay, and here you see this is really for derivatives, because here you have always a derivative, and this is dt k plus 1. So you always have a derivative. So it's not contradicting the fact that the v is going to a constant.
Christophe, sorry, and what is capital M?
Sorry?
Capital M.
Sorry. Capital M, good question. I think it could be anything, right. Any number. So with that, I mean that if you fix alpha and k, I think you can get this rate for any M. Yeah.
Okay. Thank you.
Yeah, thank you. And okay, so so what enables to get the speed of convergence is a Poincaré inequality for the degenerate gradient. Okay, so for any normal n, it would not be possible to get the Poincaré inequality. But if you have a Diophantine direction, you can get a Poincaré inequality, Poincaré-Wirtinger inequality. So you control the phi minus the mean of phi in L2 by the degenerate gradient at the price of losing some derivatives. So here you lose some derivatives of phi. But still, this is really the key to getting a rate of convergence. And this is really the place where we use the Diophantine or the non-resonance of n. And so the speed of convergence you get, let me just go back to this, by calling the left-hand side f of t and getting a sort of differential inequality on f of t.
Sorry, sorry, Christophe. I missed what grad theta is exactly.
What? Sorry.
Grad theta. How grad theta depends on theta? Grad with the index theta.
Okay. Sorry. So this is just the gradient in the variable theta. So it's a vector. So it's the nabla. So d.
Right. Okay.
Up to d.
Oh, sorry. Theta is a variable on the torus.
Exactly.
Right.
Exactly.
Okay.
So this is the true gradient, if you want to grade.
Okay.
But then you have this matrix n, which is d minus 1. So nt is
it's okay. Yeah.
D
Yeah. Sorry.
D.
Yeah.
And so you get a degenerate nt gradient.
And the Poincare inequality is somehow, well, n is fixed, right?
Yeah. N is fixed. N is really depending on small n. So just
but this inequality is still uniform in the sense that this constant c does not depend on a or kappa or n, right?
So this constant c does not depend on the does not depend on the coefficients. So so it's a functional inequality here. There is no the equation does not play a role at all here. It's functional inequality, and the capital A here, you see that one is the one from the Diophantine condition.
Yeah, I understand. But see, the point is uniformity, right, with respect to the parameters, or
right. Yeah. So the C is not going to depend on n or
right.
Yeah, that's true.
Okay.
And just a word to say that this method of proof is coming from this idea of Kozlov that I was mentioning before to construct a quasi-periodic structure, quasi-periodic cell characters. Okay. So now I will that I explained how to how to analyze the half space problem. I will explain how to glue things together, because we saw that we have an infinity of homogenization problem. And so if we want to do quantitative analysis, we'll have to carefully choose the ends and glue certain half space problems together. Okay, so the theorem Jarava and Masmoudi got in this direction is also from 2012. So they get, as I told you before, an error estimate in L2 with these rates of convergence in D equal 2 and D equal 3. They identified their homogenized equation, in particular the G bar, and they proved that the homogenized boundary data is bounded. And all this holds, it's not written here, but it holds for uniformly convex omega. So typically the disk or ball in dimension 3. So this was really a breakthrough result, because before that, as far as I know, the things that were understood were the periodic case, and it was not really understood how these half space problems, which are completely natural, interact with the geometry. So so what they did was the idea of the proof was to decompose the boundary into some boxes, and for each box you choose one point with a good direction, and so you consider the half space problem relative to this point. And what they do is take boxes that are of the same size, okay? And the union of the boxes then forms the boundary. But one key thing in the approach is chop the boundary by same size boxes, and replace in each of these box the program in the curve domain by the program in the half space, which is a completely natural thing to do, but more difficult to implement. So let me say a word about how the Diophantine condition interacts with the geometry. And in particular, let us look at let's say the 2D situation, where I consider so my normals, so the ends, they live in the one-dimensional sphere, so S1. Okay, so for any n, you know it's a vector of modulus 1, so it's an element of that sphere. So now you have rational normals, irrational normals, you have resonant normals, non-resonant normals, etc. So let us just have a look on that sphere. So what I'm saying here, and what I want to stress, is that, for example, if you look at this psi, which is E2, so which is pointing in the vertical direction. So psi, of course, is rational. So the A of n is 0, because the points of ZD lie on n-perp, on the hyperplane orthogonal to n. So this A of n, A of E2 will be 0. And what I'm saying is that there is a whole region close to E2 where the A will be small. And we can quantify that region, okay? And actually, this E2, as well as E1, or minus E1 or minus E2, are the normals for which the zone where A is small is the largest, okay? Because the modulus of the psi here is 1. So if you write n in terms of psi over modulus of psi with the GCD of psi, which is 1, then here psi is already with a GCD equal to 1, and it's of modulus 1. And that's why this region where A is small is largest. And we will come back to this later, but this is playing a key role. If you remember the computer simulation that I showed you before of Annukainen, that was showing a non-uniform boundary layer size. And this non-uniform boundary layer size is exactly coming from here. So now if you look for T sufficiently small, and if you look at all the normals which live in the sphere minus balls of certain size around these normals, okay, you know that the A will be large outside of these regions. So around each rational region, rational direction, you have a region where the A is small, and so outside of that region, the A will be large, and we will be interested in the regions where A is large, because these are the regions where we have the fast convergence. Okay, so typically in regions close to E2, with normal close to E2, we'll have a large boundary layer, while in regions with a modulus of psi prime or modulus of psi double prime large, the boundary layer is going to be small. Okay. So now, if you use this estimate, you can compute the size of the set where A is large. Sorry, the size of the set where A minus 1 is large, so A is small. And this set will be of surface measure in the sphere, which is bounded by T to the 1 minus T. So that means that A lives in this weak LD minus 1 space. So this is a computation that works for the unit ball, and that will also work in a uniformly convex domain. And this estimate for A, that A is in this weak LD minus 1 space, is really a crucial point in our analysis. And this explains why the result of Gérard Varret and Masmoudi, but also our result holds in domains which are uniformly convex, for which you have this quantification of the A, of the function A. All right. So this is just to explain that the optimal rates for the homogenization problem are known since a work by Alexanian, Chagolian, and Follin. And they study specific examples that give these rates of convergence. So in high dimension, D bigger than 4, we have a better rate than in D equal to 2, typically. And this comes from the fact that they're typically in low dimensions, there are more bad directions. So there are more directions where the A is small, giving slow convergence. So this is the reason why so in D equal to 2 and D equal to 3, typically we have more resonant directions. So now I come to the work I did with Armstrong, Cousy, and Moura, where we're still concerned with uniformly convex domains. Everything is smooth, and we're able to get better rates of convergence than the rates of Gérard Varret and Masmoudi. So here I forgot the subscripts BL, that's a typo. And in dimension bigger than 4, we almost get the optimal rate. Here I just mentioned that it's improving the rate of Gérard Varret and Masmoudi, and I will explain why we are able to and how we do to improve that rate. And we also get a an estimate for G bar at Diophantine conditions with a constant here that depends on A, so the Diophantine, so the A from the Diophantine condition. So knowing in what space A minus 1 lives, we can say where this constant lives. Okay, so this, there is, here I mentioned the improvement of the regularity of the homogeneous boundary data. Okay, so let me come to the strategy of these quantitative estimates, and in particular the strategy of the paper with Armstrong, Cousy, and Moura. So the idea now is based on Poisson kernel representation of the boundary layer. So we'll two-scale expand the Poisson kernel. The main idea will be, contrary to Gérard Varret and Masmoudi, will be to use a non-uniform decomposition of the boundary layer. So instead of taking boxes which are all of the same size, we'll take boxes that are of different sizes, and the size of the boxes will depend on the Diophantine properties of the normals, on the non-resonance properties of the normals. And the idea would be that in each of these boxes, some bigger, some smaller, will have will approximate a problem by a problem in a half space. So the strategy that we used are actually inspired a lot of works by Zhang Shen and Jinping Zhuge, and where they were able to extend the analysis to the Neumann problem, get better rates in low dimension, get convergence results in more general domains, and also improve the boundary data. So they were really building up on our work. And so let me show some pictures about how we proceed. So the structure of the boundary layer as we see it, and which is consistent with the computer simulation of Hannukainen that I showed before, is these are non-uniform, this boundary layer with non-uniform boxes, non-uniform size. So we have to balance the error between approximating by too many hyperplanes, because if you approximate by many hyperplanes, by too many hyperplanes, you will capture normals and regions where the A of n is bad, meaning that the A will be small. Typically, if you have this unit bore, and if you approximate, for example, in the vicinity of E2, if you remember, we had the large region of bad bad normals with bad Diophantine properties. So in that region, if you approximate by many hyperplanes, you will capture these bad regions where you have slow convergence of the boundary. So this you want to avoid. And you also want to avoid approximating by too few hyperplanes, because in that case, you will get a local error in the box. You will get large boxes, and then a local error that will be big. So in the boundary layer, the only thing we need is an estimate of the size of the boundary layer. But we have no description of what is happening precisely in the boundary layer. And outside the boundary layer, what we'll need is ergodicity and convergence to boundary layer tails. So this is just a comparison between the description of Gérard Varret and Masmoudi and our description with a non-uniform chopping of the boundary. And here I record the simulation of Hanukkinen that shows this non-uniform boundary layer that is captured by our decomposition. And if you look back to this, you see that really the bad regions are the regions close to E2, E1, etc., where you have a large boundary layer. So consistently with the description that I did before. Okay, so let me skip this. This is just a particular case where you have constant coefficients, where just to explain the method, but I think we have understood that. So now the ergodic theorem that we need is an ergodic theorem to study the behavior away from the boundary. And if you have a sort of Diophantine condition, then you have a speed of convergence. So let me also skip this. The only thing here is that to get the speed of convergence arbitrarily fast, I pay a price in terms of derivatives. That is why I need everything to be smooth. Okay, so now if you have oscillating coefficients, because we base everything on the Poisson kernel formula, we need an expansion of the Poisson kernel that was proved by Keniglin and Shen. And then we need to study this oscillating factor omega epsilon close to specific directions, so the non-resonant directions. We then have this sort of integrals to look at with quasi-periodic oscillations here, and we use the non-resonance to get a speed of convergence to a boundary layer tail. And this boundary layer tail enables to define the G bar. Okay, so this G bar is a complicated weighted average of G, weighted with this omega. Okay, so let me explain a bit about how we do the decomposition of the boundary layer. So we call this Calderon-Zygmunt decomposition of the boundary layer because it's based on the stopping time argument as the Calderon-Zygmunt decomposition. And at each step, we decide between good cubes that we divide and bad cubes for which we stop the decomposition. So what we do is for a given function f defined on the boundary of B1. So you can think of f as being a minus 1, basically. You find a collection of cubes that cover the boundary, and such that for adjacent cubes, the size of cubes is comparable. And in each of these cubes, you have a good direction in that sense, the sense that there is a direction for which a minus 1 will be relatively large. Sorry, a minus 1 will be relatively small, so a will be relatively large. And eventually, what you need is a control of the bad cubes, of the number of bad cubes. Okay, so let me show you with some pictures how that works. So you start with a big cube, then at each step, you decide between the good cubes and the bad cubes. So this is the bad cubes of the first step, and the other cubes you will subdivide because they are good cubes. So you subdivide and you find the bad cubes. And then you do this again and again, and at some point you will stop. And in the end, the collection of bad cubes gives you the boundary layer. Okay, so this is a summary of the pictures, so I think I will skip this. And maybe just say one word about the continuity of the homogenized boundary condition without saying too much about the details. So continuity of the boundary condition is an important topic because it's directly related to the quality of the approximation that you get in the end. So here I was just explaining how to use the higher dimensional torus to investigate the continuity of in terms of the normal. So what you have to do is compare two boundary layer characters for different normals. So you have to compare two problems defined in different half spaces. So you lift the problem to a high dimensional torus, you get this problem. So I skipped the details because I want to go to the second part of the talk, but and it's a bit technical, but doing this, you can then redo energy estimates à la Gérard-Varenne-Massoudi and get estimates for W, which is the difference between two solutions. And this gives you, in the end, some estimates for G bar. And the estimates you get for G bar depends on A, on the space where A lives. So since A minus 1 lives in LD minus 1 infinity, it gives you this space here. Okay, and quickly, this slide showed that there was a lot of activity about improving the regularity of the homogeneous boundary data. The two first lines I already talked about. Then there was a work by Feldman and Zhang, where they proved Hölder continuity of the G bar by considering an intermediate scale boundary layer problem. They introduced a new problem which enables to study the regularity of the G bar. And Shen and Zhuge proved that actually the G bar is Lipschitz, and they do this by weighted estimates. So so now I want to come to the second part of my talk. Now I'm talking about fluids about rough bumpy boundaries, which could seem a topic which has nothing to do with what I was talking before, but there is a connection, and I will explain. Okay, so now a couple of pictures from physics and other fields, just to show that rough boundaries are really ubiquitous and everywhere in nature. So this is a transverse section of the North Atlantic Ocean. And you see there the mid-Atlantic ridge, which is here, this big mountain. So the colors are completely irrelevant for what I'm talking about. I think it's about temperature of the water. But what I'm interested in is this profile of height, of altitude. Of course, everything is compressed. So this should be the horizontal length scale should be much larger than the vertical one. But we see these high oscillations of the boundary and this roughness, which actually is not exactly the type of roughness that I was talking about in the introduction, with very small amplitude and small length scale. But there may be some parts which enter the framework that I was mentioning. Okay, so this is one example. the other example is in the inside of the Earth, between the core and the mantle, and there are some measurements and which indicate that the boundary should be, the transition zone should be rough. So this is not measurement, but computer simulation based on some modeling properties of the two fluids that you have, and that show that there is this rough fractal-like structure at the boundary. But what is interesting is that the transition between the two zones, so the core and the mantle, is actually very small. So everything is happening on some length scale of 1 meter or 2 meters. Okay, so you may say I'm considering a horizontal length scale that is also small. Okay, so that may explain why, but yeah, this structure, this fractal-like structure is striking, and there are some studies about this transition zone. Another area where roughness is important is meteorology, because we live in what is called the planetary boundary layer, which is a zone of let's say 1 kilometer. I mean, depending on the conditions, it's a zone about few hundred meters to 1 or 2 kilometers of height, where the dynamics of the meteorology and of the fluids atmosphere is highly influenced by the ground. And so here you see that different ground types have different roughness properties. And so the open sea with some wind has a roughness length. So I'm not going to define exactly what this roughness length stands for. But basically, if the Z0 is small, that is small roughness. And if Z0 is high, the roughness is big. So on the open sea, you have some waves, etc., which also count as some roughness. But in principle, the roughness is relatively small. And then everything goes up to like crops, forests, parkland, and buildings. So all these different structures on the ground have impacts on the fluid, which is the atmosphere. Another example is from the study of experimental study of turbulent fluids. And here it's actually a quite striking experiment where so let me remember how that works again exactly. So you have a couple of roughness elements which are not represented on the picture, but which are living here. And you have some inflow of fluid. So you have flowing past these elements. So it's not roughness exactly in the sense that I was mentioning before, but you have some inhomogeneities, some small elements which create some perturbation in the fluid. So if you let just the fluid flow, I think it's E, without external forcing, and if the Reynolds number of the incoming flow is sufficiently small, then you just see a laminar behavior. Now, if you add some forcing, some external forcing, the flow, so here you have no roughness elements on the bottom. And on the upper part of the fluid, you have roughness elements. So with some external forcing, you add some energy that creates some instabilities. And you see that here the flow on the bottom part of the picture becomes, or is at least transitioning to turbulence, while the upper part remains laminar. and this is at least to me really striking, because in principle you would think that a roughness element would create so it's an inhomogeneity, and you would think that would create turbulence. But actually these roughness or these inhomogeneities are more like stabilizing, have a stabilizing effect. So it's not clear at all that that this is happening in nature above rough boundaries that I was talking to you about before. But there could be something like this happening, and it's something that is, I think, worth investigating. And in particular, maybe I'm not sure, but I think that there are some applications of this for airplanes and airplane wings, and trying to suppress the turbulence by some passive mechanism. So as far as I know, there are no mathematical studies of this, but looks like a very interesting subject. Okay, so another subject or instance where this appears is zoology, and in particular, if you look at sharks. So they have these scales on their body, which have even smaller scale structures. But these scales have been, are known to reduce the drag on the shark, and they are also used in to build like swimming suits for competitors. I think now it's forbidden, but so these scales have inspired a lot of industrial applications. And so you see really this rough structure. So again, it could seem a bit surprising that these rough structures actually decrease the drag. Okay, so another instance where roughness is important is fluid structure interactions. So here I showed the example of a part of a sphere which is engineered. So you don't find this in nature, but even in nature, real bodies or spheres in fluids are not perfectly smooth, and this roughness could play a role into some properties of fluid structures interactions. So I will say a word about this in a minute. And eventually, another example is microfluidics, where roughness is really also an important topic. And in microfluidics, we often have engineered surfaces. So here we have a periodic structure which is engineered, and the study of roughness on fluids in the topic of in the domain of microfluidics is an active topic. Okay, so what I show with these examples is that bumpy boundaries are kind of everywhere, that we see that many different scales are involved, many different structures, periodic, fractal-like, many different domains, thin films, rough channels, etc. And also many different equations, many different phenomena involving many different equations. So some challenges is, so I have three points that I want to mention. So the first one is understand how turbulence is generated by boundaries. So this is a very vast topic, and of course there are many works on this, but as far as the effect of bumpy boundaries or rough boundaries is concerned, there's no clear answer, as far as I know, about how roughness influences their behavior and their behavior of the fluid. So we saw this example of their fluid past roughness elements, past some inhomogeneities, for which the inhomogeneities seem to have a more stabilizing effect, so delay the transition to turbulence. But there are other examples where the roughness seems to lower the critical rings number from transition from laminar to turbulent. So it's not clear, at least to me, really what the effect is, and it may depend on the form of the microstructure, etc. So there are many questions here which are involved and for the moment far from clear. So another instance where there is some debate is this no collision paradox. So if you have a perfectly smooth sphere that you let fall in a Stokes or Navier-Stokes fluid, surprisingly, the equation predicts that the sphere will halt after some finite time and not enter in collision with the bottom. So it's the no collision paradox, and there is work by Hilaire and Gérard Varret, where they show that if you allow from some roughness of the boundary, or if the boundary is not smooth, I mean below a certain threshold, which is C1 1/2, then collision happens. So this collision or no collision paradox seems to have a relation to the smoothness of the boundary of the object that you consider. Okay, and then there is a lot of questions about singular limits. So I just cite two instances of singular limits. For example, the vanishing viscosity limit. So where, of course, even if you have a flat boundary, there is still a lot of things to understand. But there is some preliminary work considering either slip boundary condition or fluids above rough boundaries. So in that direction, there is also a lot more to understand. And highly rotating fluids, where we can say more things, and because the limit is really more constrained by the high rotation. And there is work in particular by Gérard Varret and collaborators on this topic. Okay, so let me explain a bit about Ward laws. So let me consider the stationary Navier-Stokes equations and with no slip boundary condition on the boundary, on the rough boundary. And I have this section sigma epsilon, along which I have a flux condition. Okay, so I consider the stationary Navier-Stokes in that domain omega epsilon with incompressibility and no slip boundary condition and this flux condition. So again, what you want to do is write an ansatz for U epsilon in terms of U bar and then first order corrector. So the U bar, at the formal limit, you replace the rough boundary by a flat one, and you put no slip boundary condition on that flat boundary. So you can compute explicitly a solution, which is the Poiseuille flow. So Poiseuille flow is a shear flow solution to this boundary layer, this Navier-Stokes problem. So here it's a typo again, it's U bar, and here it's U bar 2. But this U bar does not take into account all the effect of the boundary close to this rough boundary. And in particular, you can refine the approximation by considering first order correctors. Okay, so before that, just estimates about the U bar, the difference between U epsilon and U bar by Basson and Gérard-Varret. So this works without assuming anything on the boundary, but some smoothness on the boundary. I think even Lipschitz is enough on the boundary. So there is no structure at all, which is involved here, meaning that there is no periodicity of the boundary whatsoever. And L2 U-lock is just the space where you get uniformly locally bounded L2 norms. Okay, so you have convergence of U epsilon to U bar in these L2 U-lock and H1 U-lock spaces. Okay, so but this is not the end of the story. So so U bar, so the Dirichlet boundary condition is a Wall law if you want, but it's you can improve it. And there is this widespread idea that in the fluid dynamics community that roughness favors slip. And that idea may explain why in some situations also the roughness may tame some instabilities or may lead to a flow that is more regular. So mathematically, what you want to do is replace the no slip boundary condition by a Navier slip boundary condition. So you have the non-penetration condition, and on the tangential component of the velocity, you have some slip condition with a small slip length. So this slip length, epsilon alpha, is proportional to the epsilon that is the size of the roughness profile of the boundary, and that and of course, if you take formally the limit epsilon go to 0, you find no slip, which is consistent with what we had before. But considering this small slip length may enable to improve the asymptotic expansion. So instead of considering U bar, you consider UN, which is U bar plus a boundary layer corrector. And if you have some structure on the boundary layer, so this is where we'll see the connection with the boundary layer problem that I was talking in the first part, if you have some structure of the boundary, you can study the asymptotic properties of this U1. And actually, the U1, if you have something which ensures ergodicity, will converge to a boundary layer tail, which is of the type alpha 0, and that alpha 0 is exactly the one that will give you the Navier boundary condition. So these Wall laws were again studied a lot in the periodic case by all these authors and many others that I forgot to cite. But the study in the almost periodic, quasi-periodic, or random cases is more recent and is essentially due to Gérard Varret and his collaborators. So here I just give one example of an estimate that you can get between U epsilon and UN. So the Navier approximation. And you get in L2 U log this epsilon 0.2 rate, which is optimal. And so for this, I need gamma to be quasi-periodic, and I need, again, a non-resonance condition. So I couldn't have a more general theorem with a random, putting a random structure on boundaries. And if I have some ergodicity, I would get a small o of epsilon here. And if I'm able to quantify the correlation, or to have some finite range of dependence hypothesis, I could also get this epsilon 0.2 rate. So there are several instances where we can get this rate. But in any case, what we need to get a rate here is some structural assumption of the boundary. Okay, so how do we get the boundary layer system, the system U1? We just, so if you formally Taylor expand U bar on the boundary, on the oscillating boundary, so what you saw is U bar is equal to 0 on the flat boundary. Okay, so I could have removed all these U bar here. And so I Taylor expand, I find 0, and then plus a term which comes from the fact that U bar on the oscillating boundary is not 0. Just Taylor expansion. And this Taylor expansion actually shows me what I have to correct with this U1. So the U1 will be of the form 6 phi times V, and V will solve this boundary layer problem. So here you see that we have a system, a Stokes system, which is very akin, like the systems that we were studying before in the first part of the talk. So we have a problem in a half space with some boundary condition that is oscillating. One difference is that here we have Stokes instead of an elliptic problem, but this is more of a technical issue. And another technical issue is that the boundary is not flat, it's not a hyperplane as we had before, but it's this bumpy half space. Okay, so the point of view that we take in my work with collaborators, so Carlos Koenig and Jinping Zhuge, is to look at this problem from the point of view of regularity theory. So regularity theory is really describing the local behavior of solutions to PDEs, and our main point is to prove certain regularity estimates in singular domains. So we'll see some improved regularity estimates at large scales, and remove structure assumptions on the boundary function. And actually the estimates we'll prove can be read as local error estimates also. Okay, so let me say some words about large-scale regularity and homogenization. And here I will in particular record the work of Avellaneda and Lin in the late 1980s that I was already mentioning in the first part. And these works, they were considering interior regularity for equations with periodically oscillating coefficients, and their point was to prove estimates uniform in the small parameter epsilon. So in particular, the result they prove is the uniform in epsilon Lipschitz estimate. So it's a local regularity estimate. And of course, if you directly applied Schauder regularity theory, the C0 new semi-norm of the coefficients, so this is a small a, it's typo here, would be involved. So it would be the C0 new semi-norm of a over x over epsilon, and this would be not uniform in epsilon. So uniform, I mean, classical Schauder theory gives you non-uniform estimates. So to get the uniform estimates, you need an argument that is really relying on homogenization. So there are two approaches to get these uniform estimates. So the first approach is based on the idea of compactness, and is inspired by De Giorgi and Almgren in their work on minimal surfaces. And this is the approach that was used by Avellaneda and Lin. So it's basically in 3 steps. The first step is the improvement step based on improvement of flatness. So with that, I mean that in the limit epsilon go to 0, you converge to the homogenized boundary, the homogenized equation. So for the homogenized equation, you have a constant coefficient, so as much regularity as you like. And then the idea is to transfer this back to the original equation with oscillating coefficients by a contradiction argument. So you get some estimate at some scale theta, and then you need to downscale this estimate. So get the estimate at smaller scale. And at the very small scale, microscopic scale, you use classical regularity, because if you zoom at the micro scale, you don't have high oscillations anymore. So very often in what follows, we'll just skip the last step. And especially the iteration step requires correctors. Okay, so the second type of approach is a quantitative approach, so which was pioneered by Armstrong and Smart, and then reused very often, which is based on a suboptimal error estimates between u epsilon and u bar, and then again iteration. So the quantitative method was reused many times, and it's particularly interesting because it enables to deal with cases where you lose information in the limit, and in particular cases where you have multiple scales or high contrast materials, etc., etc. So unfortunately, I will not talk about this quantitative method more in this talk, but what you can keep in mind is that there are these two approaches to get the large-scale regularity or the uniform regularity in epsilon. and that this quantitative approach is enables to handle many situations. And in particular, work of Zhangwei Shen really relies on this in many works. Okay, and these uniform estimates, they are very important because they enable to get large-scale estimates of fundamental solutions, green and Poisson kernels, and also Poisson kernel expansions that were used in the first part of the talk. Okay. So very quickly, in the work of Avellaneda and Lin, we not only had the interior estimate, but also boundary estimate. In particular, that LP estimate that I was talking about before for the boundary layer problem. And so this works in C1 alpha domains, and in the Rafa domain, Lipschitz and C1, there's this series of works by Koenig, Lin, and Shen, and partly by a subset of these three authors. Okay. So let me come to the subject of the study of this boundary layer problem over bumpy boundaries. So as I mentioned in the first part, and if you have a quasi-periodic structure, you can lift the problem in a high-dimensional cylinder, T2 times 0 infinity. So once again, you get this. So here we're talking about the boundary layer problem, which was posed in the bumpy half space, and the original equation is Stokes' equation. And here, with the process of lifting the problem to the high-dimensional cylinder, we get a Stokes system, but with these degenerate derivatives. So you get again this elliptic part and the pressure part and the incompressibility condition, which all involve this degenerate derivative, and also the Dirichlet boundary condition, because I lifted the boundary condition. So now, as you are familiar with this problem, now we can study the well-posedness of the problem. And to study the convergence speed to the boundary layer tail, we need an additional assumption, which is a non-resonance condition, which is exactly this one. So here it's kappa bigger than 1 because we're in dimension 2. And this is the condition that we were talking about in the first part. Okay, so so now you can also take the point of view of staying in the real physical space and studying the boundary layer problem in the bumpy half space. So without relying on the quasi-periodic structure. So of course, if I don't rely on the quasi-periodic structure, and if I don't assume any structure on the boundary function, I will be able to say less. So I will be able to say less things on the boundary layer. But my interest here is in just the well-posedness of this system and trying to get solutions with gradients in L2. So my goal is this Stokes problem in the bumpy half space without having any assumption on gamma beyond gamma is Lipschitz. So the difficulties is that, of course, I'm not able to use any Fourier analysis up to the boundary. I have no compactness because I have no structure assumption on gamma that would enable to to reduce to a compact setting. So I have no Poincaré inequalities, but etc., etc. And the data here, the gamma a priori is not decaying because my gamma is just Lipschitz. So, so I cite a lot Gérard Barré in this talk because he actually inspired a lot of the study of this kind of problems. And in a work with Mass Moody, they introduced a method to study the well-posedness of this problem without any structure. And the method relies on decomposing this bumpy half space into two parts, one raft channel. So the raft channel will be a channel close to the raft boundary that is bounded in the vertical direction. And there we have a Poincaré inequality. Okay, we can do energy estimate. And this study, this kind of problems was initiated by Ladizhenskaya and Solonikov. The second part is a flat half space where you can just rely on green kernel estimates. And to connect the two, you have an interface where you have a non-local boundary condition, which involves a Dirichlet-Neumann operator. So actually, what you will do is transform this problem into an equivalent problem posed in the raft channel with this Dirichlet boundary condition. Dirichlet-Neumann boundary condition that connects, that kind of solves the upper half space. Okay, so the technique is very flexible and used for in other situations by myself and other collaborators. So now my equivalent boundary layer system is this system posed in the bumpy channel, which is bounded in the vertical direction. And to study the well-posedness of this system, we do energy estimates in the channel, and we have non-decaying data. So we're not expecting the solution to decay at space infinity. So the solution will live in some L2 U-log or H1 U-log space, non-localized, a space of non-localized energy. And so what we look at is these energies EK. So the energy which is contained in the box minus KK times the fluid domain. And what we want is study the growth of this EK. So typically you would like to prove that EK grows like K. And the growth of EK, you get it by a local energy inequality, which is this one, which involves EK. A K here, which is coming from the source term, which is actually the boundary condition. This term, which is coming from the cutoff that you take. And this term here, which is a non-local term, which is coming from the fact that your boundary condition here involves a non-local operator. So even if you estimate what is happening in the box minus KK, what happens outside matters. So you have to take into account this part of the energy. So this is what we call a Saint-Venant estimate, and it's some sort of, if you want, a differential, discrete differential inequality on EK. Okay, so once you have this, you can do downward induction, and you have this free parameter M that you can choose sufficiently large so that you can swallow this on the left-hand side and get an estimate for EM. Okay. and eventually you can prove that there is a unique solution such that the L2 norm of the gradient remains is bounded in that way. So it's a U-loc estimate in the sense that it's uniform in K and it's local. And this estimate is actually, so here there is a typo, it should be a V and not a U. But this estimate is all we need in the regularity estimates that I will show you in a minute. And I will finish with this topic about the improved regularity above bumpy boundaries. So I look at elliptic equations in these bumpy domains. So I'm interested in local boundary regularity. And I have a no slip boundary condition on the RAF boundary. And so the kind of estimates I'm interested in is this local Lipschitz estimate. So here, this Lipschitz estimate is an estimate at mesoscopic scale. So it's not down to the small scale. Of course, if I go down to scale smaller than epsilon, the regularity of the boundary would play a role, okay? But since I'm at scales which are bigger than epsilon, I can prove some sort of improved estimates at this scale. So I have an improved estimate at scales bigger than epsilon. Okay, so of course C is uniform epsilon. You cannot get this estimate by a classical Schauder regularity theory, and it's improved regularity on the mesoscopic scales, and there is no structure needed on the boundary function. Okay, so can we get this by just flattening the boundary? So the answer is no, because if you flatten, you will transfer the oscillations of the boundary into the coefficients, and you will get oscillating coefficients, but you have no structure on these oscillations. So you can so if you assumed gamma is periodic, you could say something, but here gamma is not assumed to be periodic. So the idea, instead of flattening the boundary, is to look at the limit when epsilon goes to 0, and when epsilon goes to 0, you converge to a flat boundary for which you have improvement of flatness because you have an equation in a flat domain, and then you can go back by compactness and an iteration. Okay, and we use the boundary layer correctors that we constructed before. Okay, so let me finish with a similar result for the Navier-Stokes equation, so the stationary problem, which I got in collaboration with Mitsuharu Higaki. And so we get a uniform mesoscopic Lipschitz estimate for this system. So it's an estimate for the nonlinear system where we are not assuming smallness of the solution, and we estimate the gradient of u epsilon at scales larger than epsilon, so the mesoscopic scales, in terms of the size of the family u epsilon in L2. So the size of this gradient estimate depends non-linearly in terms of the data of the family u epsilon. And we have that C1 of m. For small m, I think it should be a linear function. and it's increasing in M. So, okay. So there is no smallness requirement. There is no structure assumption on the boundary. And let me just mention the previous work of Gérard Varret about Hölder estimates for the linear stock system. Okay. And in addition to this, we get a mesoscopic C1 mu estimate. So again, there is no smallness condition, and we estimate the difference between u epsilon and a linear approximation at mesoscales in L2 norm. So we measure the oscillation between u epsilon and a linear approximation. Okay, and these Pn epsilon are particular. I will just say a word about this. Okay, so at mesoscales, you can read this as a C1 mu estimate, and the P epsilon nj is a linear function, which we call a Navier polynomial, because it's exactly of that form. If you assume that the boundary is periodic. So this particular form of the C1 mu estimate we get for a periodic structure. Because when the boundary is periodic, we can study the asymptotic behavior of the boundary layer and get these alpha j's. I think the analysis would work with more general structure assumptions, but what you need is determine this the boundary layer tails of the boundary layer corrector that would appear here. Okay, so these Navier polynomials, they solve their Navier-Stokes equations with a Navier-slip boundary condition. And so they are the building blocks, if in some sense, of the regularity theory of this problem. And so we see, therefore, this estimate here, which is a local estimate, as a local error estimate in some sense, and a local justification of the Ward law. Okay, so yeah, maybe I will skip these comments. If you have questions, I can come back to this. And I think I will stop here. Oops, sorry. And I thank you for your attention.